Hello everyone. In this lab, we are going to learn about performing the transient analysis in Workbench, and then we will move on with the explicit dynamic analysis. These are the contents of the lab, and first of all, I will start with the drawing of a cantilevered beam and analyze the cantilevered beam for the transient response. After that, we are going to shift to the crash test of a model vehicle, and we will analyze the response of the vehicle during crash using the explicit dynamics module. We have a cantilevered beam, and it is this time it has a dimension of 1000 millimeters. Let's suppose that the due to certain loading, the end of the beam is subjected to an initial deformation of 0.5 millimeter, and after this deformation, if the load is suddenly removed, we want to find the transient response of the beam before it settles down to a deflection of 0 millimeter. So if the beam is linear, let's solve this problem in ANSYS. Let's move on with ANSYS and see how we can find the response of the beam before it settles down using the transient module. So I will start initially with the static structure module, although it is not a general requirement, but there is a good reason and I'll show you why. First of all, I'll model the beam using the line element. It's quite simple. So this is a general beam that we have, and let's move on with the analysis. So there is one complexity that I can add is, let's say that we want to find the response initially if the deformation of the end is 0.5 millimeter, and then we can move on with the middle section of the beam and add 0.5 millimeter at the middle, and then find the response. For that, we need to split this beam into multiple edges. So for now, you can see we can only select either the edge on the left side or on the right side. We cannot add any other boundary condition in the middle. For that, we can use split edges tool in the concept and select the number split by this. So I want to divide this beam into two parts. So now we will have you will see two different edges. So the first edge is right here, then we have another edge, and we can select the vertex in the middle, so we can add the deflection at this point as well. Let's close the geometry and move on with the model. In the model, we can generate the mesh, and let's add a boundary condition. So one end of the beam is fixed. So this left vertex is fixed. And on the right vertex, let's say I am going to apply a displacement in y direction, which is minus 0.5 millimeter, and I want to see the response of the beam. Let's make it a bit more complex and add the deflection in z direction as well. It is 0.25 millimeter, so that we can see the complex behavior. So when we are adding this deflection and analyzing the response here, we can see the stresses that are going to develop in the beam. So with this deflection and using the beam tool, I can find the direct stresses here. So the maximum combined stress is about 1.5 megapascals in this case with the given deflection that we provided. And the value of a direct stress, which is the stress along the length or the normal stress, is 0. So this is the general static analysis using these deflections. As a next step, before shifting to the transient analysis, I will perform the model analysis. Model analysis in this case is not necessary, but I need to check the details of the natural frequencies so that I can specify or add the uh, step, like the time step for transient structural analysis. In this case, when the beam will be released from after applying the reflection, it will fluctuate, it will vibrate with its natural frequency. So it's a good practice to find this natural frequency and set up the steps in transient analysis based on the natural frequencies that we have. So with these boundary condition and details, I can see that the minimum frequency for this beam is about 35.7 hertz in one direction, and we can create the mode shapes and evaluate these mode shapes to see the direction of fluctuations. One another detail is to add the large deflection as on so that we can incorporate the non-linear effects as well. So I will solve this problem again with large deflection on and then resolve for the model analysis to check if there is any effect of the large deflections on the um, frequencies. So here we have the details of the frequencies now. We can see how the beam can fluctuate in different directions. So the lowest frequency is about 35 hertz and the highest frequency in first three modes is about 241 hertz. So that means the beam will vibrate about 241 times in 1 second. So it's a good practice to divide the time steps based on these frequencies. So let's say that the beam will fluctuate with a frequency of between 35 and 115 hertz because we are applying the complex displacement. So let's take 115 hertz as the upper limit, and we want to find the minimum time step. The minimum time step should be 1 divided by 115.75 hertz. So in this time period, 0.0086 seconds, the beam will complete its one fluctuation, and I must divide this into further 20, at least 20 steps so that we can capture the details of the fluctuation with time. So the time step should be less than this value. Let's divide this by 20, and there we have 0.0004 seconds, and we can use 5 seconds as well. So let's shift to the transient analysis and add the module here. So in the transient analysis, I can use the results from the model, or I can simply uh, insert it here on this model so that it is directly linked to the structural analysis. After adding the transient analysis module, you will see that we have this transient analysis module, and in this we do not I did the results of the model analysis. So I just performed the model analysis to add the value of the time step here. So how can we set up our transient analysis? I will add these, I will select these two boundary conditions in structural analysis, drag and drop these on transient so that they are copied here in this setup as well. So this is the first step. Now as a second step, I want to analyze this problem in two different steps. In the first step, uh, we will apply a displacement on the beam, and in the second step, we will release that displacement and we'll see the transient response of the beam after releasing the displacement. So I can add the number of steps here as two distinct steps. In step number one, so the current step number is one, I can add the end time here to be any value since we are applying the load here. So let's say this is 0.1 second. So in 0.1 second, the load of the displacement of 0.25 and 0.5 will be provided to the beam. And for solving this, we need to ensure that the time integration is turned on. So when we are turning on the time integration in transient analysis, that means that we are taking into consideration the inertial effects. And if we turn this off, the analysis will be reduced to the static structure analysis. So the initial time step, so at what time step we want to solve this, let's say this is 0.01. While loading, I'm not taking into consideration the minimum and maximum time steps. So let's make this minimum time step 0.01 and maximum as 0.1. Here we set up the details of the time step. Uh, take ANSYS will solve the problem for this initial time step, and then it will divide the uh, first step into further sub steps based on these time steps that we provided and solve the problem until the solution is converged. Let's move on to the current step number two. And in step number two, we will release the load so that we can observe the transient response of the beam. So in this case, I want to carry over the time step from the previous step and then add the minimum time step as 0. Let's say 0001. So 0.0001 is the minimum time step and 0.0004 is the maximum time step in this case, so that we can exactly capture the details as the beam moves. So what is the end time for which we want to analyze? Let's say I want to capture maybe 10 or 20 fluctuations until the beam settles. So I'm not sure when it will go to settle. Multiply by 10. So end time is 0. Let's make it 0.1 second. So step number one, let's make this 0.01 second here. The maximum time step, I need to decrease this to 0.01 so that it is less than the end time of the step. And I want to run the simulation for 0.1 second as the total time. So here you see that this is how the steps are divided. Now if I move to the displacement, here in the first step at time 0, we will have 0 deflection. When the time reaches to 0.01 second, the deflection will go to minus 0.5 and minus 0.25. And after that, I want to release the load. So in order to release the load, we can deactivate this step by right clicking and then clicking on activate, deactivate the step. You will see here when we activate this, the beam will be free at this point, and there will be no external loading to keep the deflection at this point. And after that, we will be able to observe the transient response of the beam. So there is one more thing. We can add the nonlinear controls and damping controls as well. So the numerical damping is set to zero point 0.1 for this material. We can also add the stiffness coefficient or mass coefficient here, or change the numerical damping to some manual value so that we can see the uh, response or vibrations damping throughout the time. Let's run the simulation here and see the total deformation for this body and run the solution. So when we will run the solution, we can see the solver output here and see the force convergence and the displacement convergence result. You will see the details of the sub steps and load steps convergence and cumulative iterations that ANSYS is performing. So as the solution is progressing, we are getting the results. Let's wait and see until the solution is complete. So after the solution is complete, we can see the response of the beam with time, and let me change the number of frames to 100 and the time to 10 seconds and run the simulation here. So this is at true scale. I can change this to uh, 2 times the auto, or let me change this to 15 times the original deflection. So this is not visible. I'll change this to uh, 60 times. So this is how the beam will be fluctuating when we will release the load. So I could have run this simulation over a larger time period so that I could have observed the damping response of this beam. You see that initially, until the step is 0.001. After this point, the free response of the beam is started. So let's extend the step to end time to 1 second and see what happens to the total deformation with time and rerun the simulation. So after the analysis, we can look at the deformation curve here and see the results. So in this case, we can see how the mixed modes appear for the deformation. So when I run this simulation here, let me change its shape to this. We are exciting this beam both in y and z direction. That is why we are seeing a combination of the behavior. So this is how this beam will be fluctuating with time when we will decrease the loading. We can increase the material damping coefficient here in analysis setting using the numerical damping controls so that this beam, the deformation, they damped early, uh, quite early after the release of the load. Uh, Finally, here in the output controls, we can change this store results at all points to equally spaced points or only the last point so that uh, we have enough space in our PC for the analysis. So we can control, we can save the results at particular points using these controls. So you can see that in the transient analysis, we do not have any limitation on the boundary condition. So you see that it can change uh, in it can change in piecewise function with time, or it could be a linear function of the time based on the constant or based on some function of a time. And we can add the value of displacement force here in based on the time steps that we have. So this way we do not have the limitation of the sinusoidal variation of the boundary conditions as it was in the harmonic analysis. So in transient analysis, the force could be any function of the time and it can be applied to the beam. So every boundary condition can be changed in this manner. Let's move on to the next problem. So ANSYS solve the problems in transient analysis module using the implicit differentiation method, implicit method. And in the implicit method, when the velocities are very large, and we need to find the details at a large number of points. So it it will take very long for ANSYS to converge to a particular solution. So in this case, we switch to the case where ANSYS is using explicit method for solving the equations, and it will take quite less time for solutions as compared to the implicit method. So implicit method is good for very small number of points where we are finding the details at low velocities or finding the response like this. However, require uh, explicit method required very short time steps, but it takes very small time to solve for the analysis, and it can give us the better result. So there is this trade-off between time of the solution and the problem type that we are solving. So in the case here that we have, so we have a model vehicle which is made of a aluminum alloy NL. So this is a non-linear material in ANSYS, and it has a shell thickness of 2 millimeter. And this vehicle comes in contact with the rigid steel bar, which is of diameter 50 millimeter and length 200 millimeter at 120 kilometer per hour speed. It is assumed that this material, aluminum, it will behave plastic, perfectly elastic, and it is torn when the plastic strain exceeded beyond 75%. We can model this vehicle as 80 millimeter wide here in this picture you can see, and it is completely made of this aluminum alloy NL, and uh, we want to analyze the response of the vehicle when it comes in contact with the rigid steel. So the first step is to model vehicle and the steel column in explicit dynamics module of the ANSYS. You can find the explicit dynamic module under the toolbox, and I can drag and drop this module here in the project schematic. After adding the module, let's go to engineering data and add the material properties. So the first material is structural steel, and since The column is rigid, so it's okay to add this steel with the elastic properties, as we will not study the changes that will occur inside the rigid column. However, the vehicle, it is made up of aluminum alloy, and the material is non-linear. So if I go to the engineering data sources and to general non-linear materials, I can see that we have this aluminum alloy NL, which means that this is a non-linear material, and I can add this to the project. So now this is added to the project. Let's look at the properties of the aluminum alloy. And here we see that instead of modeling the material as isotropic, we are modeling it as a bilinear isotropic. It has a yield strength. It is a yield strength of 2.8 into 10 power 2.8 into 10 power 8 pascals, and a tangent modulus of 5 into 10 power 8 pascals. In order for material to be elastic, perfectly plastic, its tangent modulus should be equal to 0. So if I look at the bilinear isotropic hardening curve, now this line, it becomes horizontal. And you see that when the stress approaches to this value, which is about 2.8, the material will start to deform continuously. And now we need to add what will be the value of the strain at which it will start to break. For that, I can add plastic strain failure here and insert the maximum equivalent plastic strain to be 0.75, which is 75%. So this way we have added the non-linearity based on the material properties here and the plastic strain failure. Now I can shift to the design modular and create the two parts. The first one is the steel column and the second one is the model of a vehicle. The steel column is 50 millimeter in diameter and it has a length of 200 millimeter. So the dimension is 50 millimeter, and I can extrude this about the center plane by 100 millimeters, so that the total length of this steel column is 200 millimeter. Now I can select YZ plane here and sketch the general shape of a vehicle here, and the dimensions are shown on the diagram here. I'll start with the polyline feature and add all of these lines. So let's create the general shape of the vehicle. The shape is similar to the Tesla truck. And here I can keep this as open-ended. Let's draw the arc. So the center is somewhere here. It is coincident with this point and like this. Similarly, we have another arc for the tires. And let's connect these two arcs with a line. Now I can add constraints. So both tires, they have equal radius. and I can add the dimensions. Let's start with dimensioning the tire. So the radius of the tire is 10 millimeter. This is 10 millimeter. This horizontal length is also 10 millimeter. This vertical length, this is 25. The horizontal distance between these 2 points, they are 40 millimeter. Then this dimension is 70 millimeter. Then the horizontal distance between these 2 points is 20 millimeters. Oh, it's 25 millimeter actually. And the vertical distance between these two, this is about 20 millimeter. And finally, this length is 25 millimeter. This is at 20 millimeter. So we have defined the general sketch of the vehicle, and now we need to convert this sketch into a 3D surface body like this. We can convert the sketch into the extrude using the extrude command. This is sketch number 2, and the extrude will be symmetric by 40 millimeter in both directions. So when I click on the generate, you will see a solid body will be created. I need to convert this solid body to surface body, but first of all, before converting this to a surface, I need to have the shell that uh, models the body of a vehicle. So in order to create the shell, I can use the thin slash surface command, and here I can select the faces that I want to remove. So these are the faces that I want to remove, and the thickness of the shell is about 2 millimeter. So let's do this. Now we have this solid body here of the shell, and I can rename this to a rigid pole or rigid pole, and here this is the vehicle body. If I move on with this into the model, you will see that during the meshing, ANSYS will mesh both of these objects as a 3D bodies, and I want to model this shell since it has a thickness of 2 millimeter as a surface body. So for that, I'll use the tools command here and select the mid surface. And now I can select the pairs of the surfaces. So these are the two pairs: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14 faces in total, and 7 pairs. When I click on this apply and generate, now this solid body is converted into a surface body. Let's move on to the analysis now. In the analysis setting, I see that we have both of the bodies in the project window now, and I can change the behavior of this rigid pole from flexible to rigid, as I do not want to study the deformation inside this rigid body. Second, I need to assign the material, which is aluminum alloy, to the vehicle body. And now if I go to connections, you see that we have body interactions available inside the connections. So I'll keep these as default. And if I move to the next uh, part in the tree, you will see that we can add body interaction as frictionless, bonded, frictional, and reinforcement. So I'll keep this as frictionless. We can change this to bonded. So when bonded is selected, analysis will start with the two bodies being in contact and bonded, and after that frictionless support will take over. So I'll start the analysis directly with the frictionless support and create the mesh now. So after creating the mesh, I can see that this is quite rough for now. Thickness of the vehicle is set to 2 millimeter. Let's change the sizing control here and curvature to maybe 10 and generate the mesh. So it will convert this circle into 36 parts with 10 degrees each normal angle. I can change this to 5 degrees. Since I do not want to study the deformations inside the rigid body, I can only refine the mesh of a of the vehicle, and using the body selection filter, let's change the mesh element size to 3 millimeter and generate the mesh now. So here we have quite good mesh now, and I'll proceed with the analysis with this mesh setting. So you can see that we do not have any structure analysis for the setting, so this is okay. And the initial conditions, in the initial conditions, I need to define the velocity. So the initial velocity of this body is about 120 kilometer per hour. So 120 kilometer per hour is 33.33 meters per second. I can change the unit to meters here. So this is 33.33 meters per second. And let me change this to components. So the y component is 33.33 meters per second. So this body is moving toward the pole with 120 kilometer per hour. In the analysis setting, I want to add a few details. So the first one is the total time of the simulation. So since this pole is about 50 millimeter diameter, and the velocity is 33.33 meters per second, I can check. So in 0.03 seconds, 1 meter distance will be covered. And if I want to cover a distance of 50 millimeters, so that will be 0.05 divided by 33.33. I need to run the simulation only for 1.5 millisecond. So I'll run the simulation to about 0.003, double that time, because it is possible that the vehicle may tore apart into two parts at this speed after hitting the pole, or it can rebound as well after some plastic deformation. So there are other parameters. I'll keep those as it is, as default. And finally, we have these erosion controls here. So this erosion control, it tells and says when to remove a mesh element from the body. So if the geometric strain it exceeds 1.5, which is very high value, it just removes the mesh element from that location. Or here in this case, we want the material to tore apart. If the strain reaches to 75%, I'll just change this to yes. So when the material fails under plastic deformation, so the mesh element, they need to be disappeared. So these are the general settings here for now that we can set for the analysis. Initial time step and minimum time step, all of these they are set to program control for now. And I want to analyze the deformation in the body with time, and finally the stresses that are developed in the body. Another parameter that you can control is here in the output control tab. So you can limit the results or number of points that you want to save to 10 or 5 based on the space available. So the time step in explicit dynamics is usually quite small. So I'll run the analysis now and wait until the solution is completed. Here in the solver output, you can see the estimated clock time which is remaining for the analysis. After the solution is complete, we can see that the solution converges after 14,100 cycles, and the total elapsed time is about 16 minutes for the solution. Let's look at the total deformation here. I'll change this to 10 seconds, and let me convert this to 100 frames so that we can look at the details of the simulation. And let's run this. So initially the vehicle moving at 33.3 meters per second, it comes into contact with the pole, and after some permanent deformation, which is you see which appears as a form of an indent here, the vehicle rebounds back with some velocity. And I can model the stress in the body as well, like this. So the maximum stress with time as we move forward, you see that it is at the time of impact, it reaches to about 280 megapascals, and then fluctuates as the vehicle comes into contact and rebounds. So there is this residual stress that is in the body after it rebounds. Another parameter to look at is the strain, which is the equivalent plastic strain that remains inside the body, and I can evaluate the results for the strain. And you see this the details of the indent. So the equivalent plastic strain is about 0.3. So let's look at some details from post-processing which you can use for any analysis. So the first parameter is to change the number of colors that appear. So I can either reduce the number of colors and increase the number of colors in the contours based on the analysis. Secondly, if I right click on this one, I can change the number of significant figures to 2 or 3 for this tab. I can also move this to horizontal bars here and like this, and reconvert this to vertical bar. After that, you can add the minimum and maximum value on color bars like this one. So we do not have any independent bands. I can change the color scheme to grayscale or maybe to the rainbow as well, and you can also define your own color scheme. And other post-processing parameter is the background color here, and I can change this background color from the view, from the tools under options. You will see this appearance, and in the appearance I can set the graphic style to uniform so that there is no gradient and the background color is set to white. Apart from this, these are the details for the edge colors, line colors, and number of significant figures here, and number of files that are being used. And I can also remove the logo. So when I press OK and go to the tool, you see that we have this clean version of our analysis. I can hide this pole now and see the dent that appeared in the body of the vehicle. And finally, instead of taking the snapshots, a better way to capture the details is to go here and save the image to file, or copy the image to clipboard and then paste it, so that way you will have a high resolution picture of this analysis without any additional details. You can also insert the charts, copy and paste the data in Excel. You can go to print preview and see how the details will look like, or generate the report in ANSYS. So it will capture all the solver details here in this one. So this is all about this lab. You can try with increasing the speed to, let's say, 180 kilometer per hour, and then to 200 kilometer per hour, and run the analysis and see if any ruptures occur in the shell here. Also, you can decrease the thickness to 1 millimeter and reanalyze the simulation to see the effects for this. Thank you so much for your time, and we will be back with. Thank you so much for your time. I'll be back with the next lab soon.